You ever get the feeling something's missing? Well, on a cosmic scale, you're not wrong. There's a ghost in the machine of our universe, an invisible presence that shapes entire galaxies, but that we can't see or touch or feel. So today, we're going on the hunt for this cosmic ghost.
Take a good look at this number, 85%. That is a massive majority, an absolutely overwhelming amount of something. But what is it?
That's right. Everything we see, all the stars, the planets, the nebula, the galaxies, that's just the leftover stuff. That's just 15% of the matter. The other 85% of all the stuff in the universe is completely, totally invisible.
So this huge gap in our cosmic inventory, that's what physicists call dark matter. It's the gravitational backbone of our universe, and yet it remains one of the single biggest puzzles in all of science.
So what is this stuff? Well, we know it doesn't interact with light at all, which is why we call it dark. We can't see it. But we know it's there because we can see its gravity tugging on everything we can see, from individual stars to entire galaxies. In fact, there's over 5 times more dark matter than all the normal matter combined. It's like the invisible scaffolding that holds the entire cosmic web together.
Okay, so if we can't see it, how in the world do we find it? Well, physicists have a list of suspects, and right near the top of that list is this tiny, hypothetical particle called the axion. And here's where the story gets really cool, really elegant. You see, the axion wasn't just invented out of the blue to explain dark matter. It was actually proposed decades ago to solve a completely separate, really deep puzzle in particle physics. The fact that this one little particle could potentially solve 2 huge problems at once, well, that makes it an incredibly compelling candidate.
Think of it as a cosmic 2-for-1 deal. On one side, it could be the dark matter we've all been searching for. And on the other, it could solve what's known as the strong CP problem. Now that's a whole other can of worms, but it's basically a deep question about why the strong nuclear force, the force that glues protons and neutrons together, behaves in such a perfectly symmetrical way. The axion just elegantly makes it all work. It's the kind of beautiful, efficient solution that scientists live for.
But an elegant theory isn't enough. You have to actually find the thing. And the machine that's been designed to hunt for the axion is one of the most incredible detectors ever built. You can think of it as a cosmic radio.
Right. So the theory predicts that if axions are floating all around us in our galaxy's halo, and you put them in a really powerful magnetic field, every now and then one should convert into a tiny flash of light, specifically a microwave photon. So the ADMX experiment is basically a very, very sensitive radio receiver, just slowly and methodically turning the dial, listening for that one specific faint cosmic station.
Okay, so here's the game plan. First, you start with an incredibly powerful magnetic field. We're talking 160,000 times stronger than Earth's. Inside that field, you place a cooled metal box, a resonant cavity. Now, if an axion with just the right mass happens to fly through, the theory says it'll pop into a single microwave photon. The cavity is built to resonate and amplify that exact frequency, just like a perfectly tuned guitar string. And then, all that's left is to listen for that impossibly tiny signal.
And when I say tiny, I mean unbelievably tiny. The signal they're looking for is less than a yoctowatt. That's a 1 with 24 zeros after the decimal point. A trillionth of a watt. So the real question is, how in the world do you even begin to listen for something that quiet?
Well, you need a technological miracle. Seriously, you need an amplifier so ridiculously sensitive that it operates at the absolute fundamental limit set by quantum mechanics. You need quantum ears.
And the hero of this part of the story is a device called a SQUID. That stands for Superconducting Quantum Interference Device, and it's basically the most sensitive detector of magnetic fields humanity has ever created. By using the bizarre rules of quantum mechanics, at temperatures just a fraction of a degree above absolute zero, it can pick up the tiniest signals with almost zero added noise. To give you an idea of just how mind-blowingly sensitive this is, listen to this quote from one of the scientists on the ADMX team. He said the tech is so good, quote, "Could your cell phone get 4 bars on Mars? With help from NIST, it probably could." Wow, that's the level of sensitivity we're talking about here. This is a total game changer. The older amplifiers had so much of their own internal noise, it was like trying to hear a pin drop during a rock concert. But the SQUID amplifier is 100 times quieter. This doesn't just make the experiment a little better, it makes it possible. It literally cuts the search time from centuries down to just a few years. But science never, ever stands still. Even with these amazing squids, the search is still a long, painstaking process. So of course, researchers are already designing the next generation of detectors, moving from a single quantum year to an entire quantum network.
The question becomes, how do you improve on something that's already pushing the absolute limits of physics? How do you build an even better listener?
And the answer is teamwork. Instead of relying on one single, super-sensitive detector, you use many. What scientists are doing now is building networks of individual superconducting qubits. Yep, the exact same building blocks used in quantum computers, and then linking them together. Using the magic of quantum entanglement, they can all act as one single, unified, hypersensitive antenna for dark matter.
And this network approach has some huge perks. When you link these qubits together, they become way more powerful than the sum of their parts. You can use quantum algorithms to actively tune the network, to listen for exactly the signal you want. And what's really important is that this isn't some far-off futuristic tech. It's designed to work on the kinds of quantum computers we have right now. These networks are powerful, practical, and incredibly good at filtering out all the background noise.
So here we are. We've built the most advanced radio in history to listen for a signal from the dawn of time. A signal carried by a particle that might just solve two of the deepest mysteries in all of physics. We're moving from single quantum sensors to these incredible interconnected quantum webs, all to hear the faintest whisper from the dark. The search is on, and the universe might just be about to tell us one of its greatest secrets.